Now let's come to where this gets interesting, which is talking about constrained choice. Constrained choice, which is the fact now we're going to put together your desired mix of pizza and movies with your budget, with the budget constraint, which tells you what we can really afford in terms of pizza and movies. And how are we going to do that? Okay? Well, let's go back to last lecture. What is the graphical representation of your preferences called? Indifference curve. Okay, the graphical representation of preferences is your indifference curve. It measures all sets of bundles among which you're indifferent. Okay? And the graphical representation of your constraint is the budget constraint. So we're going to ask simply, how do you make yourself as well off as possible? The answer is to find the highest possible indifference curve that you can achieve given your opportunity set. You're going to be as well off as possible at the highest possible indifference curve you can achieve given your opportunity set. Okay? And that's going to turn out to be what? The indifference curve that is tangent to the budget constraint. Okay? So if you look at figure 5.4, okay, in figure 5.4, we have the same utility function as before. U equals square root of p times m. Same one we worked with last time. Okay? And we have the initial budget constraint I just talked about, which is that y equals p times 16 plus m times 8. Okay, that's your budget. So this is our constrained maximization problem now. Okay, and we're going to talk about how to solve it graphically, then we're going to talk about how to solve it mathematically. Okay? So let's first talk about solving it graphically. So what you have here is you have a series of indifference curves that arise from that utility function u equals square root of p times m. A series of indifference curves. Now, you will choose the point that is the furthest out indifference curve that you can afford, and that will be point D. So the optimal choice, given your budget constraint and this utility function, is point D. 6 movies and 3 pizzas. And you'll choose that point because that's the furthest out indifference curve you can reach, and that will give you utility of square root of 18. Once you get square root of 18 doesn't mean anything, it's just a marker for comparison. So at that point, you'll get a utility of square root of 18. Now let's consider some alternative points and why you wouldn't choose them. So for example, point E. Someone raise their hand and tell me, why wouldn't you choose point E? Yeah?
You can't afford it.
You can't afford it. It gives you a high utility. It gives you utility of square root of 32, which is greater than square root of 18. So you'd like point E, but you can't afford it. Okay? Likewise, why wouldn't you choose point A? You can afford point A. Why wouldn't you choose point A? Someone raise their hand and tell me. Yeah.
Gives you less utility.
It's on a lower indifference curve, so you're less happy with point A. Okay? Likewise, you would the same with point B. Both of those are on the budget constraint. You can afford both of them. But at point D, your utility is square root of 18. At point A and B, your utility is square root of 10. So you're sadder. Okay? What about point C? This has the same. Point C has a marginal rate of substitution of -0.5. You're at the same. You're equivalent to point D. Why wouldn't you choose point C?
You're not using your whole budget. More is better.
We'll raise hand. Okay, appreciate the answer. But that's right. You're not using your whole budget here at point C. This is dominated because you can afford more. So the optimal point is achieved at that tangency. And we can see graphically that any other point either is unaffordable or gives a lower utility. Okay? So we want to choose the point where the slope of the indifference curve equals the slope of the budget constraint.